Our next program on digital transformation provides insights into how to begin the process with implementation tools for your company. Stephen Pratt is Chief Executive Officer at Noodle.ai. Stephen is an instigator, agitator, and pioneer in creating world-class technology services organizations. He has spent his career building innovative ways to create value for the world's most important organizations. Prior to Noodle.ai, he was responsible for all Watson implementations worldwide for IBM Global Business Services. He also was the founder and CEO of Infosys Consulting, a senior partner at Deloitte Consulting, and a technology and strategy consultant at Booz Allen and Hamilton. He twice has been selected as one of the top 25 consultants in the world by Consulting Magazine. Please welcome Stephen Pratt.
Everybody. I think my daughter wrote that, so please forgive that. So I'm excited to be here today. It's a real honor. What I want to talk to you about today is something that I think is going to transform every one of your careers. And it's something that hopefully your one takeaway is that you need to learn something about this topic, get experience in this topic, and then figure out for your executive teams and for the people around you how to get exposure to these new technologies. And the topic that I'm going to talk about is really about this new way of humans teaming with computers. It's something that wasn't possible even really 3 years ago. I like to think of April 2016 as sort of the time in which the things that I'm going to talk about today became possible. And it's been remarkably rapidly been applied in the steel industry and the aluminum industry and the scrap recycling business and a lot of other manufacturing companies and consumer products companies. And that's the topic of artificial intelligence. Just for purposes of definition, that we say artificial intelligence, machine learning, data science are basically all the same thing. And I will say that there is nothing artificial about what we're doing and what other companies are doing in this area. It's really just advanced mathematics. And so really this is applying advanced mathematics using supercomputers to very complex operations and then helping you be much better leaders in your company. So if you look at how most of us came aware of artificial intelligence, how many people remember Deep Blue, which is the IBM computer playing Garry Kasparov? How many people remember that? So a few of you, right? So this happened initially in 1996, where IBM researchers came up with the idea that they thought that they could build a computer that would be better than the world's best chess player. At the time, that was Garry Kasparov. And so they challenged him in 1996, and Garry won. And so they said, well, things are progressing fast, very, very quickly in the area of computers and mathematics and data. We've collected a lot more data on historic chess games. So they basically rewrote the algorithms, challenged him again in 1997, and this time Deep Blue won. And this was really seen as a seminal moment in what computers could do. There was no way a computer, by brute force, could calculate every possible move that you could make in a chess game. But what it did is to figure out probabilities. It learned from all the historic chess games. It learned what happened in the past. It predicted what Garry Kasparov would do in his next moves. It anticipated those moves and made better moves than the world's best chess champion. So this was really a big deal. So why am I talking about this? What does this have to do about your business? Well, your business is not chess. In fact, your business is actually a lot more complex than chess. Your company is actually more like playing 10 games simultaneously, all with different rules. It's like playing Monopoly and Life and Twister and Clue and Operation all simultaneously. And this was really not, this was just overly complex. It's more than two players. There aren't fixed rules necessarily. And this is really a vexing challenge. What happened in 2016 is that NVIDIA came out with their DGX-1 computer. The DGX-1 computer is 1,000 times more powerful than the fastest supercomputer in the world in the year 2000. So in the year 2000, there was a computer called the ASCII Red. It had crossed something called a teraflop of computing power, which means it could process a tera, which is 1,000 trillion calculations per second, and that was a really big deal. How many of those computers existed in the world? Right, there was one. It was owned by, of course, the Department of Energy, by the U.S. government, doing all kinds of spooky simulations about what happens when bombs explode. And it really wasn't practical, and no companies had access to this. So in our data center, we have something that is 1,200 times faster than that, right? And these computers are now available to people. So finally, we can take all the data that is available in very complex operations and think many moves ahead and predict things that you couldn't do before, sense patterns in your operations that you could not predict before, and make recommendations about what moves you should make in your business. And this today is very leading edge stuff. I will tell you that it will very quickly become table stakes. And I will make a forecast that certainly within 10 years, maybe within 5 years, if executives don't understand how to use these technologies, that they will be left behind, right? The company that is at the forefront of this is Amazon. That Amazon, in the way they figure out what products need to be in what places, at what time, for what customers, at what price, what recommendations they make to customers, how many drivers they have. All of those things are driven by machine learning algorithms. And you can feel it in the way that you interact with the company. So industrial data science really has traditionally been focused on two ways of modeling operations. Let's take steel production. So steel production mostly has been based on theory-based models, right? So you would have someone who would go in and understand the physics of how your steel operations work. And they would go through and they're very, very slow to develop. They're very static. Your environment is constantly changing. These models do not change accordingly and are very, very difficult to do, but very, very powerful. Next are how most companies run, in fact, how most steel and aluminum companies and recycling companies and aftermarket companies work, is that really it's empirical and empirical models and heuristics. These are fixed business rules. These are kind of rules of thumb. This is the way we've always done it. This is, well, on an average day, this was what happens. And that's how most companies are run. And I will tell you that the difference between averages and rules of thumb and the future, which is very precise predictions based on the data and mathematics, will be the difference between the winning companies and the losing companies very, very quickly. So that brings us to the third category, which is advanced data-driven techniques. What this does is takes and looks at all of the data around what's happening in your steel mill. I'll use that as an example again. It looks at what's happening in your steel mill. It looks at the chemical composition, bless you. It looks at the chemical composition of the steel. It looks at did it rain in the last week? It looks at the caster speed. It looks at all these things and makes predictions about energy consumption, makes predictions about yield. It makes predictions about will there be a caster breakout? Will there be a longitudinal crack in your operations? And allows you to act on these things. Now, these models, what's special about these models is they are constantly learning. They learn and improve every day. Every time you give the model every time you give these models more data, they actually do tighter and tighter correlations and regressions. And again, it's just math. You do very, very high dimensional correlations and regressions and classifications and clustering, and you get superior performance. So if you look at the sort of the hierarchy and the evolution of analytics within companies, what happens is you start with, oops, let me go back. Oh, let me go there. This one doesn't have a pointer. So you start with dashboards and like what happened. So most companies have this. I have my dashboard and here's what's happened historically, and that's really interesting information. You get around, you talk about it, and you say, well, let's not do that again. Or let's do that again because that was a really good thing, and you put a new business rule in place, and then that's the way it is going in the future. Then you go all the way up to things like anomaly detection, which is really what happened, and it gives you alerts on what is likely to happen. But again, these are based on business rules that someone along the way said, in my best judgment, that when the caster speed exceeds this, then that should be the top caster speed. And then you all the way get up to predictive analytics. So predictive analytics is where you start getting into machine learning, artificial intelligence, data science, and this is really using all kinds of data to say that the caster speed shouldn't be X, it should be 1.25X, right? And under these conditions. And under these other conditions, it should be 0.9X. Right? And your safety stock for your materials on these given days should be this, on these other days it should be this, right? And it's all a data-driven approach. And then you get up to prescriptive analytics, which is, okay, based on all of these predictions, which is, if you bring it back to Deep Blue, said, based on all the things that could happen, of the moves we could make and Gary could make, what's the next best move? And then it makes a recommendation. And that's what prescriptive analytics is. And then when you have these algorithms throughout your operation, then you can bring them all together and do things like maximize profit per mill hour, right? So this is the key metric. When the work that we're doing at Big River Steel is all around profit per mill hour, and this is ultimately where all these things come together. It's not we want to produce more tons of steel. It's not anything else. It's for all the hours that the mill is operating, how can we optimize our profitability? So what's the answer to this? These are some of the applications that we have available in the metals industry. So the thing in the middle is what we affectionately call the beast. So the beast is our data center that has about 200 interconnected technologies. At the core of it is an NVIDIA DGX-1, plus a lot of other supercomputers and a lot of other data processing techniques. And they're applied both on the demand side of a business and on the supply side of the business. I will tell you that actually our favorite is on the supply side of the business. We actually think applying analytics and artificial intelligence to things is much more productive than applying it on the supply side, which is more around predicting what people are going to do. It's much easier to say how metal is going to behave under certain conditions than how my son is going to behave under certain conditions, which still vexes me. So you have, on the supply side, you have materials, production, warehouse, logistics, and inventory. On the demand side, you have customer, pricing, promotions, sales, and product. In the metals industry, we don't do work in promotions or warehouse. Those seem less applicable. But you can see all the way from, like in the last presentations, around raw material sourcing, hedging. So there is still not a very good futures market for scrap steel to go into to electric arc furnaces, other than like the Turkish futures market. So we've actually built a synthetic hedge that takes a basket of tradable commodities and looks at the variance between scrap steel and finished steel, and it's something that is being used very, very effectively right now for Big River Steel. You also have things like yield management, right, which is even things like the steel width prediction. of when, like, at what point does steel come out wider or narrower than in other times. So how do you adjust the temperature of the water that's being sprayed on the coil as it's going out? So these are all really, really important things that you can take a very data-driven approach to. So if you look at laid out in a mill, this is kind of how it looks. Again, there are things like predictive maintenance is a very good one. The predictive maintenance, there are different evolutions of maintenance within a company. There is maintenance, which is after a certain number of hours or after a certain number of heats, we're going to replace key parts. This is a very, very expensive way to do things. The next is some shallow predictive maintenance, which is based on a little bit more data. What we can do is actually look at a combination of level 1 sensor data, looking at actual waveform analysis from the level 1 sensors, combine that with how many heats there have been, what the weather is, what's the type of steel being produced, and a computer will find the patterns in there and will say, when you get into these conditions, you should maintain these things. And the difference between that and just a standard way of doing maintenance can save a lot of, probably millions of dollars for a typical steel mill. So this is our rapid forensics and prediction module. It's an application that we have that says, when something goes wrong in your mill, why did it happen, right? So in the case that you don't have the data that says, we're going to predict what's going to happen, this is an application that can allow you very, very quickly to look at all the environmental conditions and say, why did this happen? So it could be all the way in the EAF. It could look at what would cause a breakout. It could do a lot of other things. It could be all the way down the caster on what's causing longitudinal cracks. Like I said before, what causes cobbling? Why did this happen? So that you can take corrective actions. And all of these are basically computers learning patterns that even the most experienced operators could not see. And I guess one very important point here is that the applications that we build are a collaboration between very experienced operators and the data science. So this is not just the computer doing the work. That the best results are when you get a very experienced operator who are basically posing questions to the computer. Say, I always wondered, that we seem to get cobbles when this happens. Could you try that? Tell me exactly, just explore that. And then the computer will find very precisely what those conditions are. That basically data science follows what we call the scientific method. The scientific method is where you have a hypothesis, and then the computer will test the hypothesis. So if somebody says, for instance, in energy prediction, that I think we use more energy for a heat when it rained last week. Could you see if that's true? The computer will go through and will find that pattern. And sure enough, we've done this for Big River Steel. It turns out that if it rained in the last week, that there's a calculatable amount. You can calculate the amount of additional electricity that will be consumed in the heats for the next week until it dries out. You can calculate based on the chemical composition of the scrap how much heat is going to be used. You can actually calculate based on who's operating the mill how much energy is going to be consumed. And it will find, putting all these things together, it will say, here is precisely the amount of electricity that will be consumed for each heat in the future. And you'd say, well, what's the big deal? Well, first of all, as you know, electricity is a huge cost component in a lot of electric arc furnaces. You can do one of two things. You can either change the production schedule and smooth it out, or depending on your contract, sometimes, like at Big River Steel, their contract actually allows them to sell electricity back to the electric grid. So just putting in this one application around electricity for prediction in Big River Steel is saving more than $5 million a year, just this one application. And that's a big deal when you talk about profit per mill hour. And of course, this has allowed Big River Steel to be incredibly successful and actually expand their operations. So this also applies in maintenance and refractories, right? If you look at, when do these things, when do the interiors of these need to be replaced? Typically, these had been done on a number of heats, and then just replace them accordingly. So as I talked about before, this is a fundamentally different place. So it looks at what were the temperatures that happened in this? What were the impurities? What were the timing? How long was it in there? And figure out all of these different things to actually come up with a much better approach to this topic. So how do you get started? So how do you actually do this? So there's a lot of different paths in this, and again, I would encourage you to dive in, right? My favorite quote from Mark Twain is the best way to get ahead is to get started. So I think that applies here, and none of you should feel bad that we didn't do this 5 years ago, because you couldn't have done this 5 years ago. But this is a very exciting time, and people are starting to do this. I think it's fantastic that it's actually happening in the metals industry. I think the metals industry could be one of the real pioneers in the application of these learning techniques in your business. I think banking is probably the furthest ahead. Consumer products is doing quite a bit. We're doing a lot with very, very large consumer products companies, mostly on the inventory side of allocating inventory, on the outbound side. If you can imagine the complexity of that problem of thousands and thousands of SKUs for tens of thousands of retail locations and constantly changing dynamics. We have one customer who they're using SAP APO to manage their inventory, and they wake up every Monday morning to 500,000 alerts, right, of things that have gone wrong in inventory around the world. And so what this is all about is actually thinking 5 moves ahead and saying, you need to fix this problem so it doesn't cause these other 10,000 problems, right? And it's made an enormous difference. It's fundamentally changed the economics of their business. So very excited. So this is basically the path that Big River Steel and some of our other metals companies have taken. So basically they start with, actually Big River Steel did not start with demand prediction. They started more with the hedging application, but a lot of the others have started with demand prediction. So this is basically planning starts with having a good demand signal. Like what is going to be the demand for what kinds of SKUs in the future, and then moving to things like sourcing and inventory management. This is how do you optimize the sourcing of inbound materials, logistics, both inbound logistics and outbound logistics. There were a lot of fines that were being incurred by a lot of these steel companies when like a barge would come and it would have to wait, and that's very expensive. So actually doing prediction of like when is the steel going to be ready, when should the barge arrive, and to save a lot of money is really important. And then moving to things like scheduling. This is production scheduling, which is enormously complex. The one thing about these algorithms is they actually thrive on complexity. The more complex, the better, right? So if it's something that the human mind can figure out and calculate precisely, or that you can do in an Excel spreadsheet, or you can do in one of your other systems, then you don't need these techniques. But if you get something that's really complex, right, that this can figure out precisely what the answer is. And then you go into production, the production process itself. And this is where you get into energy prediction, preventive maintenance, predictive maintenance, all of those types of things, which are really exciting, and so forth. And then at the end of this, you connect these things together and you run an optimization process on top of all of these, and it will fundamentally change the economics of your business. It'll lead to higher quality. If you ever wondered why we get these seemingly random defects in our steel, it can probably figure out why you're getting those seemingly random defects in your steel. If you're wondering why the width keeps varying, what led to that, it can probably fix that. If you're wondering why we have these random occurring even safety incidents, it can likely do a very good job of helping predict those things. So my, I guess, call to action for you is to get started using these techniques. You can start small. I realize this is a new thing for people. I understand that when we talk about math, that a lot of people cringe, right? But I can tell you that this is really the future. And all of you are, if I went through and asked you how many of you are using artificial intelligence today, probably very few of you would say yes. But the answer is almost every single one of you are using artificial intelligence almost every day. If you're using a navigation system in your car, you're using artificial intelligence. If you've ever used Siri or Alexa, you're using artificial intelligence. If you've ever tried to search for pictures on your phone like search for trees on my phone, and it finds all the pictures of trees, that's artificial intelligence. If you've ever ordered anything from Amazon, there are so many artificial intelligence applications embedded in Amazon that you can see the result. So I would say you're already using it more on the commercial side. It's time for this to make its leap over to the business side. And I think that the metals industry, again, I would be really, really happy if this industry were to take a leadership position in traditional industrial manufacturing in this exciting new area of technology. So thank you very much. So,
questions for Mr. Pratt? I have one quick observation. There's a good component of the crowd here that are distributors of steel and processors of steel. It's fairly apparent to see how it benefits a company like Big River Steel.
Yep.
But can you foresee applications for these other downstream businesses?
Absolutely. So I would say that when it comes to complex inventories and inbound materials and outbound logistics, if you have very complex operations in those areas, that this is tailor-made for that, right? So if you're making complex things or moving complex things, then it'll work. If it's a simple manufacturing operation, probably not applicable. If you have a low number of SKUs going to a low number of customers, you probably don't need it, right? When you start getting to a lot of SKUs or a lot of customers or a lot of modes of transportation or a lot of suppliers, a lot of things that are moving around that exceed the capacity of gut feel, then it's absolutely applicable. Yeah.
Is it costly? I imagine the more it proliferates, the cost will come down. But at this point, does a company have to be $100 million plus to even think about something like this, or is it democratized to the point where it's accessible?
It's all relative, right? It's not a $1.99 app on your iPhone, but it's not millions of dollars. So I would say typically hundreds of thousands of dollars. So the way we would, the way we see if it's a good application, and we turn down a lot of companies that want us to work with them because it's not a good fit, right? That first of all, it has to be an area in your business where there is a lot of business value. If you can make a better prediction or you can make a better recommendation, that it will typically have a 7-figure impact on your business. It has to be non-obvious. It can't be obvious. And so it has to be something that requires data to get a better answer. It's typically where you've put in a business rule as a best guess. And if that business rule were a little bit different, more precise, it would make a big difference. That's the first filter. The second filter is, do you have data that you can train the models? Again, these are not programmed. This is not software you program. These are algorithms that learn. So you feed it lots of data and basically say, find the pattern that predicts this. And it will go through and try trillions of combinations and come up with, ding, here's the right move. And the third is, can you take any action? If there's a recommendation, can you do anything about it, right? So there's a lot of cases where even if you had a really good prediction, there's no lever in the company to do anything about it. The joke there is, everyone complains about the weather, but nobody does anything about it, right? So,
Questions?
Yep.
Yeah, I had a question as to whether or not there were canned programs already for this type of process, or is it something that all these programs are written specifically for a particular application by programmers?
Right. Yeah. So there are a lot of tools that go into building these applications, and so you'll and it's the equivalent of there is a hammer and a saw and nails and wrenches and pipe wrenches and all those things that can help you build these things. There are very few companies who have put that all together and are offering a finished application, especially in fact, I think we're the only one in the metals industry right now. There are a ton of companies in the financial services industry that are doing this. You'll see fintech companies. The complexity of it is that the data that comes in is typically very messy, and so there are all kinds of technologies to get the data ready to feed into to teach an algorithm. Then there's all kinds of things for extracting what parts of the data are valuable. Then there's the actual modeling techniques, and then there's the hardening of those data, or the hardening of those applications to become a production application. And they're very unusual because they're living applications. They actually learn and improve. So it's not like you can just put a box around it and say, that's it, and it's static, right? Typical software, you put it in with your whatever best guess business rules you programmed in there, and then that's the best it ever is, and it gets worse and worse and worse and worse and worse, and then you do a forklift upgrade and update your rules, and then you go like this. The thing about machine learning algorithms is you put them in, and they get better and better and better and better, right? So there are no off-the-shelf applications in these areas. I mean, we have built a lot of applications in the metals industry. I would say that they are about when we go into a new customer, it's probably about 80% done, sometimes 70% done, because it learns your company, it learns your process, it learns your suppliers, it learns your manufacturing techniques. It's everything, all the processing is specific to your company, right? But we would say we know what data we need, we know what features are important, we know which algorithms typically work. We've already built the user interface, which is very complex also, of communicating this to the users of the applications. So anyway, that's a longer answer than you wanted.
Is the data input automatically, or is it human input?
So the selection of which data, which data sources go in is a very human endeavor right now, right? The actual, once it's selected, the ingestion of the data is automatic, right? You go through, and the first time you have to understand the data, you go through data cleansing rules, data integration, all of that. So the first time is a real pain in the butt, but once the rules are set up, then the pipelines flow automatically. And it's a constant, so we get a constant data feed from our customers. It goes through, the applications make a prediction. They also learn from the data. And they said, oh, we hadn't seen that before. That was really interesting. So let's adjust our prediction next time. But once it's up and running, it flows all the way through.
Do you, I'm over here on the other side.
Here?
Do you tie economic, way out here.
Okay, got it.
So can you tie economic models to it and start predicting what you should be manufacturing tomorrow or 2 weeks from now or 6 weeks from now?
Yes, so we do a lot of that, which is, in fact, that's the whole idea behind profit per mill hour, is looking at production scheduling of what things you should be producing to maximize your profit per mill hour. So yeah, there are some things that the systems don't do very well, which is like judging customer loyalty. So that's where the human machine partnership comes in. So the algorithm can tell you this is the optimal mix of production, of your production schedule for the whatever point in the future, and it can take into account all of the variations on prices of raw materials, even the contracts on the outside, but it can't tell you that if I piss off this customer, they're likely to leave, right? So if I can't fulfill that order, then because a lot of times, as you know, people who running businesses, sometimes it's a trade-off of, do I satisfy this customer versus this customer? It won't do a good job of that.
Yeah, just to build off the gentleman that had the question up here earlier in regards to data inputs. Big River in particular, what percentage would you say is really human input and what part is really captured? A secondary question, I guess, or close to that same question is, do you have any direct interfaces to the machines themselves, or do you have any APIs and coders that actually capture this data so that you don't have human input? The challenge we have in the mill is that guys don't want to input the data, and that's where we lose a lot of the knowledge that they have because it's slowing them down from an efficiency standpoint. So in particular, I guess my ultimate question is, from Big River, what percentage do you consider to be human input, and what percentage is considered to be technologically that you can tie into a machine?
Right. I don't know of any human input at this point. I think it's almost 100% machine input. Right? It's sensor data. It's from the operating panels. It's SMS, who's a very good partner of ours. We work a lot with SMS, so it comes from their data feeds. The part that would be really helpful is when an advanced operator sees something that looks funky, if they would write that down. Right? Because what happens is if you wait until something breaks, then you have data, right? But experience, it gets back to the question of what data do you put in, if an operator says, this is really, something funky happened here, and they write it down, then you can go back and say, what was happening? What was happening? And that becomes what's called labeled data. You'd say, I want to find that event again, right? And if you don't have those, the idea of predicting when funkiness happens again is really hard, right? And so I wish we had more data of operators logging things, but at this point it's almost all sensor data and operations data and transaction data, things that are already in your systems. Now I will say there's a lot of companies that are throwing out really valuable data. There aren't too many companies who are actually keeping level 1 sensor data. Level 1 sensor data is really, really valuable, right? So for instance, if you had a pump, right, level 1 sensor data would be what was the actual waveform of that pump. Level 2 would be RPMs. Level 3 would be probably like RPMs average for the month. So if you throw out all that other data, it's really hard to do predicting a failure based on average RPMs per month, right? But if you have waveform analysis, then you have data that a computer would thrive on. And so this is all in your PLCs and your industrial network. So we have the ability to take data from your industrial network and put it into very modern databases on a modern tech stack, and where you can do this modeling. So. Yes.
I'm just curious, once you get to the point where the model is making the recommendations, can it keep getting smarter, or at that point you use the word hardened, like is that when it's hardened and pretty much you're taking whatever's been done before and taking the best of it and that's what you do forever? Yeah,
good question. It keeps learning, right? When I say hardened would be if there's a disruption in the data feed, that it will have an alert and it will tell you something's wrong in the data feed, or if a data center goes down, that it goes over to another data center. It's things that you would expect for an enterprise level production facility. The models will keep using the new data and adjust the recommendations. I don't know, like if you look at I don't know if you know linear regressions. Like you take a bunch of dot points and you like fit a line to it. If you add more dots, you'd say, okay, I learned now that the better line is like this, right? So that's basically how it works, but it's nonlinear and in probably 1,000 dimensions.
Well, I'm thinking you have a bunch of situations, and then there's some response, and the model watches the data and sees what the response was and which responses are better and which are worse.
Right.
And I'm picturing, like in a company, a problem might repeat, and depending on which person solves it, how much sleep they got, like a million things might be solved well or poorly.
Yep.
And you would learn from that and figure out what are the best things, and we keep doing it.
Yep.
But once it gets to the point where the model is the one, it sees the situation and immediately recommends the response.
Yes.
Don't you stop getting new data and new ways, new outcomes?
Yeah, the models are not perfect, right? They're just better than what most people have now, right? So it will still make mistakes. It'll still, even on the energy prediction app, it's, whereas before it was best guess was, let's say, 50% good, this will be maybe 85%. It'll still make mistakes. In some cases it'll still be higher or lower, and it'll try to figure out why, right? And if you're talking about things like preventive maintenance, if you're fixing things before they break, then how do you get more data? If it's perfect, it will stop learning, right? So I guess yeah.
And do you, in any cases, share data? Like if there's multiple mills that are running this, would you use the data from 3 providers to make them all smarter, or is every company an individual project?
We never share data across customers, right? A lot of companies will share across their lines, right? But we will not share data across companies. So what we learn is typically what data are relevant, and what data elements are relevant. And so we would have that. We would also have the interfaces and we have the whole pipeline. So, but we will not. We don't do that. Yeah.
Thanks.
All right, we got one more. We'll take one more question over here in the center.
Yep, in the back.
I got him.
I can't hear you.
Here, while you get that one, let me get this one here.
So you mentioned earlier the difficulty in accurately modeling the human element. And then when asked by John, you said you had success predicting economic events in the form of helping optimize profit per hour at the mill.
Yep.
Can you expand on successes you've had using data science to accurately predict economic events and or like overcoming the random walk?
Right. So it is impossible to predict things like stock prices. If any of us had figured that out, we certainly wouldn't be here. So what you can do is see historic correlations between equities and how they move together, and do it better than companies are doing it now. I will tell you, it's a really, really difficult. It's a very difficult area, and it's you can get some marginal improvements on that. As far as predicting human behavior, predicting performance, predicting behavior of individual humans is, there's so much noise, thank goodness, because that's what makes us human, right? That I would say it's you can identify tendencies and things like that, and a lot of marketing and all these things, and that's where AI starts getting really scary, is when you start predicting humans and manipulating that, and like, we don't like to go there. So, but you can predict how populations behave, right? So you can, in fact, this is how insurance companies run. I mean, they do it in a very basic way. In fact, they're starting to use a lot of data science about, they can tell you pretty accurately that next year this many people are going to get the flu, or this many people are going to, that's probably a bad example, but maybe this many people are going to fall in their bathtubs, right? And it's remarkably accurate, right? Because if you average it out over a lot of things, and they're trying to say, okay, can we get even better at that by saying, the number of people that fall in bathtubs is actually, it might be related to things like the weather or the economy or all these things. And then you can build a more sophisticated model to say, here's how many people are going to fall in bathtubs. So predicting economic events, let's say tariffs, right? No way, impossible, right? Because the way the algorithms work is they need lots and lots of historic data. Now, if there had been thousands or millions of tariffs slapped on companies or countries with that correlated to certain events that were happening, and you had, centuries of data about this, and the conditions were still about the same, you could do it. But these algorithms cannot predict black swans. They can't predict one-off events. That's not the application of these technologies, right? And again, it's just the math, right? And they're very, very powerful. But there are limitations of what they can do. And I think it's I would say a core skill that executives should learn is where they're applicable, right? So it applies to this part of my business, and I'm not going to fall for the BS that it applies to this other area, because it won't work, right? So you need somebody who will tell you, like, where this will actually work. And which is why we're very, very careful on what we do. because we want everything we do to be successful, because obviously reputation is really important. So if you ask us to do something like predict your stock price 2 quarters out, like it would be a very short conversation. So.
All right, we'll take one last question, and we thank you.
So is this on, or is it this time?
Was there
it's
one?
On? Okay.
Yep, got it.
So 2 quick questions. One just being, you touched on data a little bit in your previous response, but what kind of data do you all need to really let your algorithm run itself out, learn from it? I think a problem that I've run into in the past is not having robust enough data in a B2B industry that doesn't have the robust B2C, 10 million data points.
Yep.
Second part of the question is what Noodle.ai does, is it really just the hypothesis answering, or do you all also create tools and systems that actually does demand forecasting, forward looking, and setting pricing and things along those lines?
Right, okay, thank you. Yeah, so I'll do the second one first. So we produce finished applications. So if you look at like energy prediction, we will actually give you, so Big River Steel right now, they are currently using our application. It will show them each hour what their predicted energy use will be, and where they have opportunities to resell energy, where they can also change production schedules. So we deliver the final applications, right? So basically it's data in and then finished application out. That's what Noodle.ai does. From a data, it's very dependent on the problem you're solving. You're absolutely right in a lot of B2B cases that you don't have as much data as you do in B2C cases. If companies have been collecting sensor data, there's a lot of really rich information there. Typically, if for distributors, if you're running on ERP systems, there's tons of information in your ERP systems, right? On transactions and inventory analytics is one of our favorite topics of distribution of inventory, allocation of inventory. Your ERP systems will have really, really good data for that. But you're right, in a lot of cases, if you go in and someone says, do predictive maintenance on my equipment, and I have no data because I threw it all out or I never had it in the first place, then it's okay. Well, start collecting. We can help you collect the data, or start collecting the data yourself, and then come back in 18 months. So.
All right, Steve. Thank you very much. We appreciate it.
Thank you.